Hi, and welcome to a brand new video. So today we're going to be tackling the path sum 2 problem in which we are given a root of a binary tree and an integer target sum, and we need to return all the paths from the root to a leaf node that sums up to target sum. So for example, with just this mini one, as you can see, if you start with 1, there's no possible path. Even though 2 plus 3 is 5, they're in two different branches. So what we're going to do first is we're just going to declare a global variable, and this is just going to be what we're going to return. And this is super similar to the subset 2 problem that we tackled earlier. So if you want to go watch that first, I do recommend that. So I'm just gonna create like a blank list, and I'm just gonna set it to a new list. Don't forget your import statements. I'm gonna say this dot and is list. And that's pretty simple, but that will allow us to access this through our recursive function. So I'm going to do private void recursion, and we're going to first take in a list of integers that we're going to be appending to ands. And I'm just going to call this int. And then the second thing we want to pass is the current sum. And I'm going to do this actually in reverse. So I'm going to pass in target sum, and every single time I'm going to subtract the value of the current node. So all we need to do is say when sum is equal to 0 so that we don't have to have target sum as a global variable. That's just like a me thing, but you can do it the other way around. So in sum, and then obviously you need the current node that you're at. And so in this, all you need to do really is call recursion of, let's create a blank list first and pack it in blank, target sum and root. And just like a minor thing, if root is equal to null, just return ands. This will return something blank. That's just like a base case of ours. And then here we can just return ands. So inside this recursive function, what we're going to do is we're going to say that if the current sum is, actually, let's do it the other way around. If this is a base node, which means that if root.left and root.right are both null, then we're going, so actually let's code that. If root.left is equal to null and root.right is equal to null, which means that let me put the parentheses first, which means that this is a base node, then we have two possible scenarios here. We have that sum is equal to 0, because remember we're subtracting every time, and if sum is equal to 0, then we're good to go. This is what we want. So at base like nodes, we want it to be equal to sum. So what we're going to do is we're just gonna set that we're going to append the current node to int. So append root. And we're just going to append that. Oh, whoops, not append, and that int to ands. Looks like there's an error. Oh, whoops, root.val. Perfect. And otherwise, we just need to return, because that means it didn't fit our base case, and we don't want to add that to our ands because it doesn't fit our description. So the other case is that we have it's not a base node. It is one of the intermediate nodes. It might be the root node, but it's not the base node. So I'll just call these all other nodes. And in this case, what we're going to want to do is actually, let me just do sum minus equal root dot val up here. And then what we're going to want to do is say that if, actually, I'm just going to do I think that the best decision is to do int.append root.val, and oh, I keep writing append for some reason. Root.add, and we're going to also say create a clone of this. And the reason is because since these are objects, if I don't clone it, then passing the same list into two different recursive functions, they're going to affect the same list, and obviously we don't want that. So if root.left is not equal to null, we just call recursive of ints sum and root.left. And if root.right is not equal to null, then we'll pass in the clone here. And the thing about doing this is because we already subtracted sum right at the top here. So that means we can determine whether sum is equal to 0, or we can do all of this based on the fact that we already subtracted root.val. Because we're including root.val here. So like if it's the base node, that we still have to include some this current root as a part of that. And also we need to include it here, obviously, if it's one of the nodes. Any node on the path will be included in sum, so that's why I just subtracted it at the top. So this is our code. What we did is that we first declared a global variable. This is going to be what we're going to return. We set it to something. This is our base case. And then we called recursion and returned that global variable. And then inside recursion, what we first subtracted the current node from sum, and said that if this is a base node, then if sum is equal to 0, we're going to add it to our answer. And otherwise, we're just going to return because it didn't fit our case. And then for all other nodes, we're first going to add a root.val to the current list. And also, as you can see, that repeats here and here. So to make our code more efficient, we can also just bring that out here because this is a return statement. It doesn't matter whether we add the number or not. And then that will also remove the necessity of brackets here. So we also add root.val, and if here we create a clone so that it doesn't affect the same thing, and we call recursion on the left side and the right side. So that's all we need to do. Right now I just created an example case with example 2, so I should return blank. And there we go. So hopefully this helps you solve the path sum 2 problem, and if you have any confusion, I do recommend going back and watching the subset 2 video that I created. See you in the next video. Bye!